Welcome to the lecture on fundamentals of MIMO wireless communications. We are currently discussing frequency selective fading. We have already seen how frequency selective fading Fourier transform or the transfer function has to be found out. We will now look at the frequency characteristics of the signal and that will describe or give us a full description of frequency selectivity, and we will also try to define coherence bandwidth, which is again another important parameter for such a channel propagation model. With that, we will come to a close of the small scale propagation models for a single input single output system, and after that we need to proceed towards the MIMO channels. So, now this is the model what we have started looking at. We have described this particular model in the previous lecture. We have also seen how the channel impulse response looks like. This is our standard classical description of the channel impulse response. We have seen the phase. What we have added to the description is now that description is a little more details, where we have said that the first delay as given by this is also a sum of all the delays of all the paths that come at the first delay plus all the paths coming at the second delay, and these two are getting separated because of delta function. Since tau 1 is not equal to tau 2, you cannot add them up. So, here also that delta function separation was available. So, this is what we have described in the previous lecture. We want to see the frequency domain representation. So, we want to take the Fourier transform in the delay domain, and what we have is the discrete Fourier transform is what we are taking in this case. I have also described we could take the continuous Fourier transform also, and this is how it would look like, and the expression of the Fourier transform is the one that we have here. So, yeah, this is the expression that we have. Tiny correction here would be tau 1 and tau 2. This is right over here. This is okay. This is okay over here. So, what we have here is basically the Fourier transform of the echoes coming at the first delay plus the Fourier transform of the ones coming at the second delay. So, what we last discussed is if we write in the discrete domain, we can write in the discrete domain itself. This is equal to the Fourier transform of at time t of k because of tau 1 plus h of t k because of tau 2 and so on up to Fourier transform of in the kth frequency because of tau n plus dot 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 plus Fourier transform of at time t k tau n max. That means the maximum resolvable delay. So, we just remember there are two things. One is n, which is ideally to be n tau n. So, basically the n we have used in this is ideally to be n, sorry, it is supposed to be n suffix tau n. That means the number of multipaths at the nth delay. That means the first delay could have 6 to 10 multipaths, let us say. The second delay could have different number 1, 2, 3, 4, 5, 6, 7. This is the second ellipse. The third one could have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, basically this is the third delay. So, what we can say is n tau 1, let us say in this particular example is 10, n tau 2 could be let us say 20, n tau 3 could be let us say again 15, and so this could be variation. So, that we should keep in mind, and this is the number of resolvable delays. So, we could go up to n tau 6 we could be. So, this is basically indicated by n tau max, and this is indicated by n. Ideally speaking, there should be tau n in the suffix, but we are omitting it for simplicity. So, we should keep this in mind. Okay. So, if we proceed, what we just said is if there is a single multipath, we have already seen it, what would happen, that would result in flat fading, but now we have addition of several such ones. So, what I will show you now is the frequency response picture of a sample realization. So, remember this particular one that we have over here, yeah, this particular one is a sample realization, mind it, at a function of time. So, if I say h of t prime, where t prime is not equal to t comma k, that means the kth frequency, we will get h of t prime comma, let us say tau 1 for the first path, and this is not equal to h t prime, because they are a different time instance. So, that we understand. So, same would happen with the frequency selective fading. So, that is why we say we are looking at a single snapshot. Proceed with this. Of course, we have given this description. So, now suppose I have taken one particular situation, and this situation is described by certain parameters, which is not very much necessary at this point of time. We can look at them later through an example. So, when there is only one path or one resolvable path, we have seen it is flat across frequency. So, what you are going to see is this particular one, that is in red color, across the frequency index. So, this is the frequency index, clearly the x axis, the k axis you can say, and this is the gain. That means you are basically talking of h of t comma k squared, and this is in dB. So, basically 10 log 10 of this function. Okay. So, that is the y axis, this is the x axis. Whereas, so if we describe it shortly, we have taken a bandwidth of 20 megahertz, RMS this 50 nanosecond as the spacing, and RMS delay spread of 10 nanosecond. We will describe more of this. So, this is what we get. If we move further, what we get is the second situation, where we say the delay spread has increased. If you look at this, the delay spread has increased in this particular case. So, I go back a little bit, allow me. Yeah. So, in the second case, what we have is delay spread from 10 nanosecond has increased to 50 nanosecond. What does that mean? Previously, suppose this is an echo, this is an impulse that I have sent. The delay spread is very small, delay spread is very small, and this width is 10 nanosecond. Whereas, in the second case, where it is 50, this number is 50. So, if I clear it up, if you look at this number here, I take a different color. If this is readable, 10 and 50, the second one is 50. In that case, let the first echo come over here, and then there are echoes. So, this width is now 50 nanosecond. So, how can this be 50 nanosecond? This can be 50 nanosecond if the reflectors or scatterers are spread in such a way that if this is the transmitter, this is the receiver, if this is an ellipse. In the first case, everything is almost here in the first case. In the second case, reflectors are slightly oriented in a way where there are multi paths which are having longer delays. So, this is 50 nanosecond, right. So, that means the spread is more. If the spread is more, we are going to add up more resolvable paths. That means, if we look at the previous picture, that means we are getting more resolvable paths. We are getting more resolvable paths, as we are saying this plus this. So, more and more. So, this gets added. If delay is less, you have only one, you have flat. If there are more number of paths, that means delays are more number of resolvable delays. If tau 1, tau 2 and so on, if this increases, this spread increases. So, as this spread increases, what we get is the situation represented by this particular figure, by this plot, that is the frequency response that is happening. If we move on further and we say that we have a possibility where I am erasing this for visibility, and yes, now we have the scene for 100 nanosecond, which I will try to explain with a different color. So, if it is 100 nanosecond, it means that the response due to an impulse is launched at here, is echoes are coming till 100 nanosecond. So, that means echoes are coming for 100 nanosecond. So, rather it should be black in color, which is indicated by this black line. So, if I would draw it with corresponding colors, we could have a better picture. In the sense that the first one, I would say echo, the impulse launched, the echoes are here. So, this gap is 10 nanosecond. The second case, I would choose a different color and say that echoes are now spread to 50 nanosecond, right. In the third case, which is indicated by the black one, I would have echoes which are coming from far away places. That means there are reflectors or scatterers which are located far away. So, this distance is 100 nanosecond. This means that we have more things to add up. That means we will have what we have is h of the Fourier transform of h of t at that frequency at delay tau 1 plus Fourier transform of h at time t 1 h k at tau 2, and this for the red case is only limited to 1, for the blue case it is possibly limited to 2, for the black case it is possibly limited to 3 or 4, that means h t 1 comma tau 4, let us say, and so on. And as we increase this length, this line is now having tau, the delay spread as 1000. So, that means the impulse, if we could draw with, let us say, yellow color. No, yellow is probably not nicely visible with this violet color, let us say. Echo starts here, echoes keep coming for, and it goes on for a duration when this distance goes beyond this particular screen is 1000 nanosecond. So, that means you will have several such things getting added, plus dot 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 Fourier transform of h 1 h t 1 comma tau, let us say 20, that means there are 20 resolvable multipaths, for example. So, what we observe is as we increase this delay, what we are getting is for the first case, when there was a single resolvable delay, there was a flat fading. The second case, when there are, let us say 2 or little bit close to 2, we have somewhat variability in the frequency domain. That means some wide portion of the frequency is getting selectively passed through while the others are not. In the next case, what we have is this particular contour indicating that there is some portion of the frequency which is getting signals not attenuated much, whereas there is another portion where the signal is attenuated heavily. The third case that we are going to see is, or the fourth case is when the signal is fluctuating according to the line that I am tracing. The screen has become very, very dirty. So, there is much more fluctuation in the frequency domain. There is selectivity. These shaded bands are the ones which are having less attenuation. They are passing the signal properly, whereas this region is having attenuation, let us say relative attenuation. So, what we see is as we increase the paths or as we increase the delay, the selectivity in the frequency range in the frequency increases. That means there is more crossing, there is more number of crossings. So, if we have a threshold in the frequency axis, there is more number of crossing, and some portions of the frequency axis, this is the frequency axis, are selectively allowing the signals to pass through, and hence this is known as frequency selective fading. In the same tone, I would like to mention that the time selective fading, there it was instead of t, instead of k, that was the time axis, and things looked very similar, and we had a time selective fading. In time selective fading, what we remember, we had discussed certain portion of the time signals were passing through with less attenuation, certain portion there was more attenuation, and we described level crossing rate and average duration of fade. So, here also similar thing applies in the frequency domain, and we move quickly to the description. So, along with this multipath power delay profile, we would describe with something known as the coherence bandwidth. This is very, very important. So, coherence bandwidth is described as the portion of bandwidth where the signal remains coherent with itself. Just like we have defined coherence time, now we are defining it in the frequency domain. That means signal is coherent in the frequency domain. If I take two frequencies f1 and f2, over these two frequencies, if the signal is quite same, that means if h of t1, let us say it is the time, and instead of f let me take k1, that means one of the frequencies is almost equal to h of time and k2, that is what we have used k. That means this k1 and k2 are within the coherence bandwidth. We have a way of defining it. As of now we will describe it very briefly. There are many detailed description to this also. So, what we clearly see in the previous slide, in the previous picture, what we have seen is as your number of paths increase or as your delay increases, your frequency selectivity increases. So, as your delay increases, naturally the delay spread is going to increase. So, as your delay spread is increasing, the coherence of the signal across the bandwidth decreases. So, if we take the first case, coherence across this entire bandwidth is there. So, coherence bandwidth is very large and delay spread is very, very small, because there is hardly any spread in the delay. In the second case, what we have is in the frequency domain there is somewhat fluctuation, delay is little bit more. In the frequency domain the coherence has reduced. If we take the black case, then there is more delay, that means it has become 100 from previous case of 50 and 10. The coherence in the frequency axis is less now, that can be visibly seen over here. And as we move to the case of 1000, what we clearly see is that coherence bandwidth visibly it has become less. So, one way of quantifying, this is another way of describing the frequency selectivity of the channel. One is RMS delay spread, the other is this particular definition of coherence bandwidth, where coherence bandwidth is defined as inversely proportional to RMS delay spread, and there are two coherence bandwidth descriptions, the 50% coherence bandwidth description and the 90% coherence bandwidth descriptions. These are exactly similar to the coherence time descriptions, philosophically they are the same. So, the 50% coherence bandwidth is given by this expression 1 by 5 times tau RMS, and 90% coherence bandwidth is 1 over 50 times RMS tau RMS. That means, once we calculate the delay spread, 1 divided by 50 times RMS delay spread is basically the portion of bandwidth where signal is 90% correlated with each other, whereas 1 by 5 tau RMS is the portion of the bandwidth where signal is 50% correlated with each other. So, two important definitions. If we want the signal to be nearly constant across frequency, we would find the bandwidth given by 90% coherence bandwidth. This 90% coherence bandwidth is across which the signal is nearly flat. So, over this bandwidth you have flat fading, you can say, that is a good approximation. Over the 50% coherence bandwidth there is some similarity, but there is some variation also in the signal. So, with RMS delay spread and with coherence bandwidth, we can describe the channel characteristics of a frequency selective fading. Okay. Just to support this whatever we have discussed, this particular slide contains some results taken from papers which are from Donald Cox and others, and this particular picture represents, this particular picture shows us the x axis as delay spread. So, that means tau RMS, and this axis is the coherence bandwidth at 50% coherence bandwidth, see 0.5 correlation, this 50% coherence bandwidth. So, one is the measured versus some theoretical description of it. What we clearly see is as the delay spread increases, the coherence bandwidth decreases. So, what you see over here is as, so if we look at this portion, delay spread is large, coherence bandwidth is small, large delay spread, small coherence bandwidth. If we look at this portion of the curve, delay spread is small, coherence bandwidth is large. This is matching measurements with theoretical values. This is the 90% coherence bandwidth description. Again, it is quite similar what you say for large delay spread, smaller coherence bandwidth, smaller delay spread, larger coherence bandwidth. So, that is as per our description and matching with results, and this is for this 910 megahertz urban mobile radio channel. So, that means in the city area a 910 megahertz of center frequency. So, what we see is that these descriptions are supported by measurements also. So, we are actually following a proper model, we are not without a model. finally, towards the end, of course, there are many things to discuss, but we will directly go into something known as the scatter plot. What we talk about in this particular slide is the total description of the channel in the delay Doppler domain. So, that means we have seen the delay domain, that is the tau axis. See, these are all tau axis, tau is mentioned over here, this we have seen, the tau axis. What I had drawn previously was the time axis. That means I have drawn the time axis, and I had said that signal would fluctuate in time. This is the tau axis. At another delay, signal is going to fluctuate in time. At another delay, signal would fluctuate in time. Another delay, signal would fluctuate in time. Now, we said that this delay could have 10 multipaths, this delay could have 20, this could have 15, and so on and so forth. Also, this delay could have a p theta which is equal to 1 by 2 pi, whereas this one could be the one which has a specular component. This one could have a different p theta which is not equal to 1 by 2 pi. They could be different. Now, p theta affects the Doppler, that is what we have seen, because while calculating the Doppler, we were calculating phi of h of delta t. While we calculated phi of h of delta t, we had E of theta. Now, while having E of theta, we made the assumption that let g of theta, that means antenna gain, equals to 1 and p theta equals to 1 by 2 pi, that is a 2D isotropic scattering model, and there we said this gives rise to J spectrum. That is what we had seen before. So, here instead of this time variation which is fluctuating in time, if we look at the Doppler spectrum, which we expect to be remaining static over a region and over a certain duration of time, because it is the second order statistics, it is not the instantaneous coefficients. So, this is one way of looking at the channel. So, in the tau axis, we will take a look at the average power. In the frequency axis, we will take a look at the spectrum. So, what we see in this particular picture, which is the rural area diagram, where it says at the first echo, the Doppler spectrum is a Jx, along with it there is a specular component, that means it is Rice, it is a Rician. At the second delay, which is at 0.2 microsecond, we have a Jx spectrum, and so on and so forth. Whereas, if we take a look at an opposite one, I mean these are also similar, this and these are similar. So, we take a look at another one. There are a lot of echoes coming in very short duration, and after a very large duration, if you look at this, is around 15 to 20 microsecond, whereas this is around 0.6 microsecond. This is because it is a hilly region, there is a hill, across far away there is another hill. So, it takes long time for the signal to get reflected and come back to the receiver. This is the mobile, this is the transmitter, right. So, in the reflectors which are close by, because there are, let us say, houses around the mobile, for example, things get scattered almost quite well from all directions. What you have is a Jx spectrum, because in these cases p theta is equal to 1 by 2 pi, whereas here the one that comes reflected from a far away reflector, which could be a hill, it is cos, indicating it is not, p theta is not equal to 1 by 2 pi. That means, the probability of rays coming from all directions is not equal, the rays are coming from a specific direction, and the spectrum is given by the Gauss spectrum, which we had seen earlier. So, with this kind of a diagram, you can almost completely characterize the single input single output channel, and look at what would be the signal experiencing. There are many details to it, but because of course our interest, we would limit ourselves to this. Without this description, it is difficult to proceed with other things, but this is just the initial part of it. There are many more details which can be studied. We would simply like to stop at this point with a very short description that we have seen the small scale fading, where we have seen time selective, frequency selective. In time, we have seen slow fading and fast fading. Slow fading is one where coherence time is greater than symbol duration. Fast fading is one where coherence time is smaller than symbol duration. In frequency selective fading, we have seen there are two cases. One is flat, one is frequency selective. Flat is the case which we could define as the coherence bandwidth is larger than the system bandwidth, and frequency selective is the case where coherence bandwidth is smaller than the system bandwidth. That means within the system bandwidth, if this is your system bandwidth, channel fluctuates in frequency, and this is the case within the system bandwidth, the channel is nearly constant, it is fluctuating later. Here within the symbol duration, channel is nearly constant. Here beyond the symbol duration or within the symbol duration, the signal is fluctuating. With this, we would bring our discussion on frequency selective and frequency flat fading channels towards an end. There would be certain numericals which we will try to provide as additional material which would be useful for this particular part. Thank you.